In this lesson, we are going to start Unit C, which is our polynomial functions unit. In this unit, what we're going to be learning is how to factor polynomials that have a degree higher than 2, and we're also going to be graphing these polynomials. So, to start, let's first define what a polynomial function is. You guys have already seen polynomial functions that have a degree of 2 quite often. This is something like this. This is a polynomial function of degree 2. All that we're going to do now is we're going to increase the degree of these functions, and we're going to work with cubic functions, quartic functions, and a few quintic functions. So that's degree 3, 4, and 5. This notation here is just showing you that in a polynomial function, we have a coefficient times x to the power, and this highest power is the degree of the function, plus another coefficient times x to 1 power less. So for example here, we've got a power of 2, the next term has a power of 1, and then the last term has a power of 0. So these powers are decreasing. So if this was a cubic function, we would have x to the power of 3, x to the power of 2, x to the power of 1, and finally a constant on the end. So that's all that this is showing. And in these polynomial functions, the key things to remember is that n, or our exponents, all have to be whole numbers. We're not dealing with fractional exponents. X is a variable. The coefficients are going to be real numbers. And the term on the end, this a0, is a constant. This can be any number, but it has no variable. Remember that constant can also be equal to 0. The degree of the function, as I was saying, is the highest power. So in this example, this quadratic is of degree 2. If I had a cubic function, it would be degree 3. And the leading coefficient, a base n, is the coefficient that's in front of the highest power. We call that the leading coefficient, and it tells us a great deal about the polynomial function that we're working with. So, you are already familiar with 3 types of polynomial functions. The first type is one that we don't see too often, but you definitely should be familiar with, and that is a constant function. A constant function has degree 0. So in this case, this equation could be something like y equals 2. It's just a straight horizontal line. We say that has degree 0 because there are no terms with an x in them. Compared to a linear function that has a degree of 1, where we have something like x minus 1 or 3x plus 6, any kind of linear function in the form mx plus b. And we also have seen lots and lots of quadratic functions where the degree is 2. And we know that this shape is a parabola. So now we are going to introduce some new shapes into our repertoire for graphing. The first is a cubic function, a quartic function, and a quintic function. And I'm going to show you some basics about these functions. When we're talking about functions, we can get some key, polynomial functions, I should say, we can get some key information from 2 parts of our polynomial function. The first is the degree, because the degree will tell us the shape of the graph. And the second is the leading coefficient, because it will tell us something called the end behavior of our graph. So what quadrant our graph is moving to and from. So I'm going to start with the graph of y equals x. We know that this graph is a diagonal line that goes from quadrant 3 and extends up to quadrant 1. We also know that if we change this to y equals negative x, that the slope is changing. And so now our graph is going to go from quadrant 2 to quadrant 4. We know that about linear graphs. And what's nice about this is that we can apply these similar characteristics to cubic functions, because in linear functions our degree is 1, which is odd, and in cubic functions our degree is 3, which is also odd. And a cubic function looks like this. If that leading coefficient, so this is positive, it's going to also extend from quadrant 3 to quadrant 1. And if I change it to be negative x cubed, it will flip and extend from quadrant 2 to quadrant 4. So the degree of both of these, or of all of these I should say, is odd. And when it's a positive a value in front, we go from quadrant 3 to quadrant 1. And when it's a negative, we go from quadrant 2 to quadrant 4. This applies to all polynomial functions that have an odd degree. And I've summarized that for you on the next page. So you can see here, odd degree polynomial functions have, if they have a leading coefficient that's positive, we go from quadrant 3 to quadrant 1. If it's an odd degree and it's a negative leading coefficient, we go from quadrant 2 to quadrant 4. This is true for linear functions, cubic functions, quintic functions, which have a degree 5, functions with a degree of 7, 9, 11, etc. Any odd degreed function. We can do something similar when we're talking about even degree polynomial functions. For even degree polynomial functions, and I'm going to show you an example using quadratics. So in quadratic functions, give a sec a little bit. We'll come back to these characteristics in 1 second. The most common even degree polynomial function is y equals x squared. And we know that y equals x squared looks like a parabola on the origin. This goes from quadrant 2 to quadrant 1. If I change this to negative x squared, we know that this flips downward, and now we go from quadrant 3 to quadrant 4. The same is true when we have x to the power of 4. This graph goes from quadrant 2 to quadrant 1. You'll just notice that there's this little bit of variation in the middle of the graph, but the end behavior where this graph extends from and goes to is the same. And surprise, surprise, the same is true if we change the leading coefficient to negative. This graph is going to flip upside down and go from quadrant 3 to quadrant 4. So these are our basic shapes. So if we summarize that and we put it in a table, you'll see here, if we have an even degree polynomial function, so a power of 2, 4, 6, 8, 10, 98, any positive number, if the leading coefficient, any even number, if the leading coefficient is positive, we're going from quadrant 2 to quadrant 1, just like a parabola that opens up. And if it's negative, we're going from quadrant 3 to quadrant 4, just like a parabola that opens downward. So if we look at the characteristics of these functions, and I'm going to go back up to our odd degree functions for a minute, When we start thinking about the characteristics in terms of intercepts and maximums and minimums of these functions, you'll notice here that in odd degree polynomial functions, all of these functions, y equals x cubed, y equals negative x, y equals negative x cubed, these all have at least one x-intercept. And that's true for all odd degree polynomial functions. They will definitely have at least one x-intercept, because in order to go from quadrant 2 to quadrant 1 or 2 to 4, you must go through the x-axis. So they have to have an x-intercept. Now you'll notice in a cubic function, sometimes they will have multiple. So for example, this one that I drew here has 3 x-intercepts. So when we're talking in general, we can say that our odd degree polynomial functions have at least one x-intercept up to a maximum of n x-intercepts. And n is the degree. So for example, in a cubic function, the degree is 3. I can have up to 3 x-intercepts. A cubic function may also only have one x-intercept, and it may also only have 2. And you'll see what that looks like when we start graphing these. Also, these odd degree polynomial functions always have a y-intercept that's at the constant. They always have a domain of xer and a range of yer, and that's because they're extending infinitely in opposite directions. And these have no maximum or minimum. They extend upward and downward infinitely. When we compare that to even degree polynomials, in even degree polynomials, sometimes we have no x-intercepts. Because these even degree polynomials go from quadrant 2 to quadrant 1 or 3 to 4, they don't always touch the x-axis. And we learned this when you were in grade 11 and you were learning about parabolas. Remember that our parabolas can have no x-intercepts if they are above the axis. They can have one x-intercept, like this one, because it lands right on the axis. Or they can also have 2 x-intercepts if their vertex is not at y equals 0. So we've got 3 options there. So even degree polynomials can have 0 up to a maximum of n x-intercepts, where n is the degree. So for example, a quadratic function has a degree of 2. It can have 0, 1, or 2 x-intercepts. A quartic function of degree 4 could have 0, 1, 2, 3, or 4 x-intercepts. These polynomial functions of even degree also have y-intercepts that are at the constant. Their domain is always xer because they extend left and right infinitely, but these functions have a maximum or a minimum. So you'll see here this quadratic has a minimum at 0. This one does as well. And so the range is going to go from that minimum and extend upward, or like in this case, from this maximum downward. So those are the general characteristics of polynomial functions. When we flip over to the next page, we've got a couple examples here. So in these examples, I've asked you to identify the type of function and its degree, its end behavior, the possible number of intercepts, whether it has a max or a min, and to state the y-intercept. So if you look at example 1, this is a cubic function, which is an odd degree. The leading coefficient is negative, so because it is an odd degree polynomial with a negative leading coefficient, it's going to go from quadrant 2 to quadrant 4. Because it's an odd degree, it's definitely going to have at least one x-intercept, but it could have up to 3. So 1, 2, or 3 x-intercepts. It won't have a maximum or a minimum because it's an odd degree, and its y-intercept is at the constant, which is just at 4. I also substituted x equals 0 here for the y-intercept, but you don't really have to. It's just this number. For part B, we have a quartic function, so a degree of 4, which is even. Because it's even, and the leading coefficient, the a value here, is just positive 1, it's going to go from quadrant 2 to 1. It's an even degree, so it will have anywhere from 0 up to the degree, so 4 x-intercepts. This one doesn't have a constant that's written, but remember, that means the constant is actually 0, so the y-intercept is 0, and this function would have a minimum because it's going from quadrant 2, so it's going from quadrant 2 and leaving in quadrant 1. We don't know what the middle of the graph looks like, but we do know that it's going to extend upward. So that means that whatever happens in here is going to be a minimum. Finally, in example 2, there's actually just one little typo that you need to fix. In your notes, this says minus 60. Please change that to plus 60. This question is talking about this function for volume, which is related to an ice sculpture. So Bill is preparing to make an ice sculpture, and he has a block of ice that he's trying to reduce the size of. And he's removing the same amount off of each of the 3 dimensions. The volume of the block is represented with this function here, where x is the amount in centimeters that he's removing from each dimension. So remember, volume is a function of length times width times height. So when you calculate the volume of this block, this is the function that represents it, where x is the amount that's taken off of each. So first, this asks what's the degree of the function. Well, the degree is 3. That's the highest power. B asks what the constant represents in this context. Well, remember the constant in this context is when x equals 0, right? The volume will be 60. So in this case, since x represents the amount removed, and we're saying that the volume is 60 when x is 0, it means the constant is the volume when 0 units are removed. So really, it's the block that he's starting with. The end behavior of this function, we have a negative leading coefficient and an odd degree. So we're going from quadrant 2 to quadrant 4. The x-intercepts in this case, remember the x-intercepts are when y equals 0, or in our case, volume equals 0. So that's what those x-intercepts are going to represent. And it's asking what is the volume if he removes 2 centimeters from each dimension. So I plugged in 2 for each of these x values and solved. So it's 6 centimeters cubed when we remove 2 centimeters from the length, from the width, and from the height.